Okay, we're continuing on here through chapter 2 to finish it up, hopefully. We've been talking about at the end there quantum numbers and sort of the relationship quantum numbers to electron configuration, and really where we do find electrons in the atom and these atomic orbitals. And we use quantum numbers to help us understand, what orbitals we would find on sort of what energy level. Reminder, there's really 4 quantum numbers. There are N, which is the principal quantum number, and that basically is sort of the energy level. And it could have values of like 1 through 7. We have L, which is the angular quantum number, and that can have values of 0 to n minus 1. These basically tell us sort of the shapes, if you will, of the atomic orbitals, 0 being an S, a 1 being a P, a 2 being a D, and so forth as you go through there. We also have M sub L, which is the next quantum number, which could run from minus L to 0 to plus L. And for the lack of a better description, it will tell you pretty much how many different orbitals there are for that particular atomic orbital. It's really going to tell you the sort of 3-dimensional space at which those orbitals are hanging out. And then we have the spin quantum number, which is plus or minus a half, and that is basically the orientation of those electrons within an orbital. And again, upwards is denoted as plus a half, sort of downward is denoted as sort of minus a half. So going through this, we were able to determine sort of on for example, the first energy level, the only available option. If n equals 1, L would equal 0, which is an s orbital, and m sub L would equal 0, which means there's only one orbital or s orbital. And obviously you could put a couple of electrons in that particular orbital, so it could be plus or minus a half. Any questions on that there? We saw the different orbitals that we really deal with electron configuration. We have s orbitals, which there's only one type of s orbital, which means it can hold a maximum of 2 electrons. There are p orbitals, which are 3 different types of p orbitals, and that could hold a maximum of 6 electrons if you fill up the subshell. D orbitals, there are 5 different types. Each one could hold 2, which is a maximum of 10 electrons if you fill up the entire d orbitals. And F's, there are 7, which gives you 14 electrons if you fill them all up. So we're now going to talk a little bit about electron configuration as well, and sort of tie these two together here. So one important part about electron configuration is electrons will basically go in from lowest energy to highest. And in the absence of, for example, just one electron, for example, all the energy of the orbitals are equal. So what I mean by that is if we took like the 3rd energy level here, with only one electron, all those orbitals are pretty much going to be exactly equal with energy. What happens though, as you put in more electrons in there, you have negative things kind of hanging out with each other. There's actually some changes that occur in the energy of the orbitals, and that obviously affects the order at which the electrons go into the atom. The major difference actually happens right around here at the D and the S. When we have more than one electron, basically the s orbital there, the 4s orbital, is actually going to be lower in energy than the 3d, and that means that it actually will get the electrons first as it gets filled into the atom, followed by the 3d, and that pattern follows all the way through. After that, kind of the s's come first before the d's in terms of getting the electrons. So there is a way you could sort of remember the order here. We could do basically, we know that on the first energy level, there's s orbitals. On the second energy level, there's p orbitals. On the 3rd energy level, there's d orbitals. And on the 4th energy level, that again is where we start to see the f orbitals happen. What you could do is essentially just fill in the numbers underneath. And this essentially is the order at which electrons go into the atom. We always start up on top here, and then we basically follow the arrows. And this will give you the proper order as you continue down this way. Again, a major difference is, as we can see here, we are going to go to the 4s after the 3p and then back to the D. So again, that pattern always sort of follows. The S's get the electrons first. Once again, we always start up here and basically work our way across each of those as we continue through. So let us do some electron configuration here. Make sure everybody's on the same page. We'll start with, a pretty simple one there. And we will go with hydrogen here. Hydrogen's atomic number is 1, which means it has 1 proton and would also have 1 electron. So starting up here, we would start with 1s1. The first number here is the principal quantum number. That is the orbital at which the electron's hanging out in, or subshell. And that is how many electrons there are in that particular orbital or subshell. So that is the right way to say it, 1s1. It is a superscript for the one on top. There's no dashes, there's no commas, there's no weird things that people like to write here. So ratio here would be 1s1. We also represent electron configuration by what is known as the orbital diagram. And the orbital diagram typically uses boxes or lines and arrows to represent the electrons. So in this particular case, we would do a box, which is our 1s orbital. And again, the very first electron always goes in the upward direction there. And that would be the orbital diagram there for hydrogen. Any questions on that? Our quantum numbers here for this particular electron would be what? N would equal what here? N would equal 1. This is on the first energy level. L would equal? It would equal 0 because it's an s orbital, right? M sub L here would be 0, as that's your only option for it. And the spin here, quantum number, would be plus 1/2. So these would be basically the 4 quantum numbers for that particular electron hanging out there for hydrogen. Any questions on that there? Yeah. So the top one says that. Other questions? Yeah. I can if I figure out which one it is. Let's see. Oops. Better? Yeah. Good. Yep. Okay. Then let's continue on here. We're going to then go to helium next, which is 2. So helium is 2. Once again, we would start at the very top here. It would be 1s2 in this case. That would be the electron configuration for helium. And if we drew the orbital diagram for this guy here, we would have a 1s. We would put our first electron in there. For our second electron, we do have a couple of options. We could perhaps put it in like this. We could put it in like this. And there really is a rule as to what we want to follow in this case. And this is what is known as the Pauli exclusion rule. And basically the Pauli exclusion rule says that no 2 electrons in the same orbital can have the same 4 quantum numbers. So basically what that means is we cannot put our second electron in there the exact same way. Otherwise, it will end up with the exact same 4 quantum numbers, which means we can't do that. That means that really our next electron does need to go in the opposite direction. And if we do the quantum numbers for that electron right there, we will end up with N here for this guy would be 1. L would be 0 because it's still an s orbital. M sub L here would be 0. And the way we get around through Pauli's exclusion rule is with the electron heading in the opposite direction in terms of its spin, that has minus 1/2 in terms of its spin quantum number. And that does not violate basically Pauli's exclusion rule. So when you're drawing orbital diagrams, basically the first electron goes in up, the other electron goes in down, gives it an opposite spin, and also does not violate it because with a slight difference of the spin quantum number, they end up with 2 different quantum numbers or 4 different, not the same set of 4, basically. Any questions on that there? Okay, so continuing on here to lithium, which is 3. It would be 1s2, obviously, from looking at our diagram here. We cannot put any more into our box. So that means this is done. We then need to zigzag back and come to our next orbital, which would be the 2s. And it would be then 2s1 here. Once again, you can count the numbers up on top, and that tells you the total number of electrons have been distributed. That's 2 and 1, which is 3. In this case, we have 2 electrons on the first energy level and 1 on the second energy level. Now, if we did our orbital diagram here, and just to save space, I'm just going to go side by side. Technically speaking, the 2s should be higher in energy than the 1s box there. We're going to go our first one in, second one down. Once again, here, our first one here will go right there in the upwards direction. And if we do our 4 quantum numbers for this guy, what would n equal in this case? N would equal 2 in this case, since it's on the second energy level. L would equal, well, you have 2 options here. You have L could equal 0 or 1 in this case. And in this case, L would actually equal 0 because this is in a s orbital. So this is the value that you have. Would not be 1 because 1 would represent a p orbital, which is not where this electron is. The m sub L here would be 0, as that's the only option you could get with an L that's equal to 0. And our spin quantum number here would be plus 1/2. Any questions on how I got those numbers there? Yeah. It would not, because the difference there would be the n value. N would be 1 for it, and then n here would be 2. Yeah. Other questions? All right, continuing on here, rolling with a little beryllium action. Once again, we could see we could actually put 1 more electron in there. So we will go and fill that orbital 1s2, 2s2. Once again, looking at the top number, it says 4 electrons that we have filled. So we'll have our 2 boxes, again, not drawn correct in terms of energy, but for space here, 1 up, 1 down, 1 up, and now 1 down. Looking at our quantum numbers here for the 4th electron that went in. Once again, it is on the second energy level. So n would equal 2. It is an s orbital, which means the correct value for L will again be 0 in this case. M sub L would be 0, and M sub S in this case would be minus 1/2, as we're specifically talking about that second electron that rolled in there. Any questions on that one there? All right, continuing on then. Number 5, which is boron. As we can see here, we have definitely went through our 2, so we're going to follow our arrow back. Next orbital there is going to be 2p coming through there. So we will go 1s2, 2s2, 2p1. Once again, here, if we count up top numbers, 2, 2, and 1, it's 5 electrons we have distributed. In this case, if we do a little orbital diagram, we will have our 1s, our 2s, and now because it is a p subshell, there really should be 3 boxes for our 3 different p orbitals, our px or py, and our pz orbital, our x, y, and z actually. Putting in our electrons, 1 up, 1 down, 1 up, 1 down. First one will go over here into that box right there in the upwards direction. If we look at our quantum numbers for this guy here, n would equal what in this case? N is going to equal 2 as we're on the second energy level. L would equal, L in this case would equal 1. Again, you have an option of 0 or 1, but because we're specifically talking about the electron in the p orbital, the L value has to be 1. Once again, an L value of 0 is an s orbital, a 1 is a p orbital, a 2 is a d orbital, a 3 is an f orbital, alphabetical after that as you continue on. That means our m sub L in this case would be what? It would be -1 in this case, as this is -1, 0, m plus 1, which represents the px, py, and pz orbital in this particular case. And our m sub s here, I'll put it over here, is going to be +1/2. Any questions on any of those there? Yeah. It is because for any L value that you have, so in this case, we have options of say 0 and 1 in this case, m sub L will go from -L to 0 to +L. And in this case, that means -1, 0, and +1. And it actually just goes in order of the boxes there. And that represents, in this particular case, the px, the py, and the pz orbital in each of those. Yeah. Other questions? All right, so that is boron. Carbon next. Let's do a little carbon action here. So carbon would be 6. Maybe carbon would be 6. Carbon will be 6. So it's going to be 1s2, 2s2, 2p2 in this case. Once again, looking at our orbital diagram, 1s box, 2s box, or line, if you like lines better, or 2p subshell. Going up, going down, going up, going down, going up. Now, there's another important rule that happens when we get into a subshell where there are multiple orbitals, and that is what is referred to in common circles as Hund's rule. And basically, Hund's rule says the most stable arrangement for orbitals is to maximize parallel spins. So to maximize parallel spins is sort of the ultimate goal, a little bit more stable. Couple of terminology here. Our spins here, say in this first orbital, they are going opposite of each other. They're what are sometimes referred to as paired spin. Those guys are paired off. They basically cancel each other out in a sense. Parallel spins means that the spins of the electron are basically going in the same direction. And since our notation is usually up, the next electron should go in the next orbital in the upward direction to maximize the parallel spin. So basically, when you have multiple orbitals in a subshell, you basically go up, up, up until you get to the end, and then you go back and start pairing everybody off. That will maximize your parallel spin and the correct way to do it. Any questions on that there? Yeah. So let's see, let's do it. So if we're looking at this guy and his quantum number, n would equal what? 2. L here would equal, once again, it would equal 1 as it's a p orbital. The m sub L in this case would actually be 0, and that's going to be the difference between the electron in front of it that has a -1 for that one. It's basically hanging out on the py orbital here as opposed to the px orbital. And then obviously the ms here would be +1/2. Any questions on that there? All right, might as well continue on, finish out the first little row there. Nitrogen is next, which is 7. So we would have 1s2, 2s2, 2p3. Once again here, doing our orbital diagram. Up, down, and to maximize our parallel spin, we're now going to put that third electron over there in that third orbital. That is going to give us, for our quantum numbers for this guy, n is equal to 2 once again, which is on the second energy level. It's also still in the p orbital, so L would equal 1. In this case, it's now -1, 0, and over to the pz orbital, or the +1 in this case. M sub s here is now going to be +1/2. Any questions on that one there? At this point, we have no other options, right, other than to start pairing them up, right? At this point, we cannot maximize any more parallel spins with our p subshell. We actually still have 3 more spots to sort of fill up in the p subshell before it's completely filled. So let us fill those spots here with oxygen, which is 8. Will be 1s2, 2s2, 2p4. Once again, putting in our guys. We go parallel first. Now we're going to come back to the first orbital and pair up the spin there, giving this last electron that we put in there n is equal to 2, L is equal to 1. M sub L is now back to -1 as it's back in the px orbital, but our spin here going to be -1/2, which is going to make it different than our first electron that went into that particular orbital. Any questions on that there? All right, then we have fluorine, which is 9. Finished up there, it's a helium. Fluorine is 9. 1s2, 2s2, 2p5. And doing our orbital diagram here. S. We're going to go up, down, up, down, up, 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 down, and down. And lastly, here, our neon here will be 10. So we obviously have 1 more spot for an electron here. And we would go 1s2, 2s2, 2p6 in this case. And that would obviously at this point fill in all of that subshell. At this point, if we did have more electrons, it is off to the 3s orbital at this point to put it in there. Any questions on that there? Now you can follow this electron configuration for pretty much everybody that you need, and it's something you can recreate pretty easily for yourself. Again, like I did, you basically just start with 1s and go down to 7 basically. Then you go to the p's, we start on the 2, go down to 7. And you start at the D's, which is 3, and go down actually to 6 as needed. And then our F start on that 4th energy level in this case. Once again, you always start at the top and again, keep zigzagging your way back. There is sort of an exception to normal electron configuration. For example, if we look at something, actually we'll get there in just a sec. Why don't we do one here? Why don't you do the electron configuration for, do it for iron. And iron is number 26. And why don't you give the 4 quantum numbers as well for the, let's do the 22nd electron. So just write the electron configuration. You don't have to do the orbital diagram. So write electron configuration and give the 4 quantum numbers. Once again, you don't need to draw the orbital diagram. That is what is scheduled right now, 1 week from today, I think. Feels good. I like it. Okay, let's take a look. So electron configuration here would be 1s2, 2s2, 2p6. At this point, if we count up the top numbers, I got 10 working, so I got to continue on. So next would be our 3s2. Need to continue on to our 3p6. Now remember, at this point, that is sort of where the difference happens. It's actually the 4s2 that should come first, as they are lower in energy, and we'll get the electrons. Then we are still short. At this point, we're at 20. So then we do need to go to our 3D next, and that would nail us a 3d6, I think, in this case. Any question on the electron configuration there? Now, when we look at this, right, we are looking for the 22nd electron. So if we just sort of count up the top here, we can see where the 22nd electron's at. That is 2, 4, 10, 12, 18, 20. That means that our 22nd electron is actually hanging out in the d orbitals in this case. And if it's helped you to visualize it, you could draw your boxes for your d orbitals, which should be 5 boxes, by the way. And they would feel just like the p orbitals. So first electron here would go there, second, third, fourth, fifth, and now 6 would roll here. So that would be really the way that the d orbitals would be filled in. We are up to 20 before we get to the d orbitals. So 20, this guy right here would be 21. That would then be 22, which should be the second electron that is hanging out there. And that means that that is really the quantum number that we're looking for here, the 4 for that particular electron, which would be our 22nd electron. The end value here would be 3 in this case, because we are on the 3rd energy level here where these orbitals are hanging out. Because our n is equal to 3, that means our L value could be 0, 1, or 2. Which one is the correct one here? It is 2, as that does represent the d orbital. So our L value should be 2. Because our L value could be 2, our M sub L value could go from -2, -1, 0, +1, and +2, which, by the way, pretty much just runs on this like this: -2, -1, 0, +1, and +2, which means that our electron is actually in the -1, and it is going upwards, which means our spin should be +1/2. You can see you get very, very specific in terms of the quantum numbers for each individual electron. Yes. you wouldn't start with the spin down, it always goes up. Yeah, so when it goes into the orbital, always by notation, it's always spin up first, and then when it pairs off, spin down. Other questions? Okay, so in this case, it might be helpful to visualize what electron you're talking about by just sort of drawing the last set of orbitals there in an orbital diagram so you can see how they go in. Plus or minus 1/2, and this particular question would be incorrect because it's specifically talking about that electron that's pointing upwards, which should only be plus 1/2. Now, if you had a generic one where it just said, give the 4 quantum numbers for an electron hanging out in like a d orbital, since you're not really talking about a specific electron, it would be acceptable to go plus or minus 1/2 on that one, because you could be talking about the one that goes up or the one that goes down. Other questions? All right, so clearly you need to be able to write electron configuration. You need to be able to figure out quantum numbers. Any questions on any of that there? Why we have this here, another important sort of aspect of electron configuration is sometimes we do use sort of a shorthand when we're writing electron configuration. So we'll just use iron's electron configuration. If we take iron's electron configuration up to here, basically. So we take its electron configuration up to here. That is how many total electrons? That is 18 electrons, right? If we just count the top numbers there, before I made a nice decorative on it there. And if we look at the periodic table, number 18 is our good friend Argon. So it's sort of a shorthand is we could put Argon in brackets, and that basically indicates the electron configuration for Argon. And then we would continue on with the rest of the electron configuration. This would be 4s2, 3d6. Argon is group 8 on the periodic table, and those are our noble gases. This is sometimes referred to as noble gas configuration. And pretty much what that means is you could only do it using the noble gases that come right before the element. So what goes in that bracket has to be a noble gas, and then you just continue on with the configuration at that point. So, if we did sodium, which is 11, it would be 1s2, 2s2, 2p6, 3s1. This part of the configuration is 10 electrons, which means that is neon, which is our noble gas number 10. And then continuing on here with our configuration, 3s1. So it always has to be the noble gas that comes right before the element to do that. It's a nice little shorthand, so you don't have to write everything out. Any questions on that there? Now, I was talking about earlier that there are several exceptions that occur in terms of normal electron configuration that experimentally they've found, these things are a little bit more stable in a different sort of electron configuration. 2 main exceptions that most people usually talk about is our friend chromium, which is 24, and our friend copper, which is 29 in this particular case. And if you follow sort of the zigzag approach there to electron configuration, you would end up with 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. And if you did copper, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. And the exception that happens here is pretty similar in both of them. It actually occurs here at the end. And it's been found experimentally that they are more stable with 1 extra electron up in the d orbital and 1 less in the s orbital. So our correct sort of configuration, 1s2, 2s2, 2p6, 3s2, 3p6, 4s1 3d5. So that basically puts a single electron in the d orbitals, all heading in the same direction, parallel, a little bit more stable. Same sort of exception over here at copper, 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. That's going to pair up everybody there in the d orbitals in this particular case. Obviously, as well, you could do your sort of shorthand on that there. Argon, 4s1, 3d5. Same thing here. Argon, 4s1, 3d10 in this particular case. So those are two common exceptions that you should know. We're going to see a slide, I think, in a bit. But if you look on the periodic table below chromium and below copper, there's a lot of exceptions like that in there. Like silver, for example, also similar exception. PD there has actually no electrons in the s orbital. They've all been sort of promoted up to the d orbital. The reason it's able to do that is the proximity of these orbitals. They are super close in energy, so it doesn't take a lot for those electrons to kind of move from one energy level to the next. Upon filling the electrons, it goes to the 4s first, followed by the 3d. They're very close in terms of energy. What actually happens, in case you're not aware, is as you fill the d orbitals with electrons, there's actually a switch in terms of the energy level of those orbitals, and the 4s actually becomes higher in energy than the 3d. So these guys are very close in energy to begin with. There's actually a switch in energy that occurs as you start filling the 3d orbitals with electrons. And that is why you will sometimes see people write electron configuration like 1s2, 2s2, 2p6, 3s2, 3p6, 3d5, 4s2, and put it all in order. And that's the electron configuration based on energy. Nobody does that really in chemistry classes like ours. We always write it based on filling, which means the 4s should come first, followed by the 3d. But you'll sometimes see people write it the other way, and that's really based on energy after the electrons have gone in, and there's that switch that occurs. I only took one upper level class that they actually wanted you to write it the opposite way. So we always go this way, and that's the way you should do it in here. 4s first, followed by the 3d. But again, if you see it the other way, that's usually based on energy. Question? Yeah, so there's just that sort of really swap in energy that occurs. So, you know, as they start filling, there's a lot more electrons, so they kind of move themselves a little bit further down, and the less electrons kind of move themselves a little up. And that happens all the way through on all the sort of s's and the d orbitals there. And that also affects when transition metals, which are right there in the middle, when they lose electrons, which electrons they actually lose first in that case, which is different than representative elements when they lose electrons. Other questions on that there? So let's talk a little about that, what happens when something obviously gains or loses electrons. So if we have something like magnesium with a +2 charge, if we look at the electron configuration for magnesium with no charge, it has 12 electrons, and that would be 1s2, 2s2, 2p6, 3s2. There's really two types of electrons we're dealing with here. These guys right here, which are lower energy level electrons. We have electrons on the first energy level, electrons on the second energy level, and we have electrons on the third energy level, which is further away from the nucleus. These guys are what are referred to as core electrons. The guys that are closest to the nucleus, lower in energy. And these guys are our favorite guys, which are our valence electrons. And these are the highest energy electrons. They are furthest away from the nucleus. They're also held not as tightly. And they're really the ones that get lost and are involved in bonding. So when we're dealing with bonding, it's always the valence electrons because they're further away from the nucleus. So when this guy becomes a +2 charge, the plus means it lost electrons, 2 is how many it lost, which means it will end up with 10 electrons, which means the electron configuration for magnesium with a +2 charge would be 1s2, 2s2, 2p6 in this particular case. The 2 electrons would be these 2 valence electrons that basically were lost in that process. If we look at something like oxygen, which can gain a -2 charge, we did electron configuration for oxygen with no charge, which is 8. 1s2, 2s2, 2p4. When it has a -2 charge, it means it has now 10 electrons, gained 2 electrons. It has the spot for those 2 electrons right there in its valence electrons and those orbitals. And it would give you 1s2, 2s2, 2p6, which is 10 electrons. Who else on the periodic table is 10 electrons? It is neon, same electron configuration as neon. All 3 of those things, magnesium with a +2 charge, oxygen with a -2 charge, and neon, they all have the same electron configuration. They are what are referred to as being isoelectronic with each other. So isoelectronic means that they have the same electron configuration. This is pretty much the basis of all bonding, ionic bonding, covalent bonding, is pretty much everybody wants to get to the same electron configuration as a noble gas. And how representative elements do it, representative elements are outside the transition metal, which is dead in the center. They lose and gain electrons, either lose electrons to go backwards to the noble gas that comes before them in terms of electron configuration, or they gain electrons to go forward to the noble gas in front of them to gain the right number of electrons. Noble gases are chemically inert, they are stable, and they're really what everybody wants to get there. An ionic compound, that's what happens. Somebody loses electrons, somebody gains electrons. To do that in covalent bonding, as we'll talk about, is done through sharing of electrons, is basically how they all kind of get to that electron configuration. Any questions on that there? Now, as we saw, transition metals are a little bit different. When transition metals lose electrons, because of that switch in energy, it is different how they lose electrons. So we just did iron, which was, again, our 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d6. When iron has a +2 charge, that means instead of 26 electrons, it should actually only have 24 electrons. The electrons that always go first for iron and all the transition metals are going to be these s electrons, because they actually end up being higher in energy, as we just talked about, once we start filling up to d orbitals. So in this case, what happens is, because at this point, the electrons look something like this. In this case, the first 2 electrons that will go will be those 4s. So the electron configuration here would be 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. Or if you want to do a little notation there, argon, 3d6. Again, the 4s electrons always go. Now, if iron got to a +3 charge, that means it would actually have 23 electrons. In this case, we would take the 2 electrons from the 4s. Now I still need 1 more electron, right? Now I go into the d. So the d would be the next highest in energy, and we would grab an electron out of the d, and we would end up with 1s2, 2s2, 2p6, 3s2, 3p6, 3d5 are argon 3d5. So transition metals are a little bit different than representative metals, which is basically lithium, sodium, potassium, magnesium, those guys, aluminum. When they lose electrons to become charged, they do not end up at the noble gases. They will basically just kind of lose those s orbitals, electrons first, followed by d orbitals if necessary. Because if you think about it logically, they would have to lose in most cases a lot of electrons to get themselves back to a noble gas. So if you look at something like zinc, which is at the end of that row, you know, he's like 3d10. You would have to shell like a 12 electrons off to get back there. You don't usually see like a zinc with the plus 12 charge. So it doesn't usually happen in most cases. So they really don't end up back over there at a noble gas. Any questions on that there? I'm sorry? Well, so we're going to talk about, but typically metals will pretty much lose electrons. They typically are not the ones that want to gain electrons. Non-metals are the ones that really want to kind of gain electrons. So metals to the left, right, of that like staircase, non-metals to the top. So non-metals like nitrogen, oxygen, fluorine, they will gain and kind of go forward. On the left-hand side there, sodium, magnesium, calcium, even aluminum, those guys, when they lose electrons, they will back up to the noble gas code before. Other questions? Yeah, so for the most part, when you get into sort of the metalloids, in most cases, they're going to kind of behave more like a non-metal, which means they're going to end up kind of sharing electrons. They're in a lot of cases, they'll sort of share electrons. So it depends on which one, but a lot of them are almost treated like non-metals in a lot of cases. Other questions? Okay. So we try a couple here. What is the electron configuration for? Let's do calcium with a +2. Let's do bromine with a -1. Let's do a nickel with a +4 charge. Yeah, you can just write the electron configuration. It's good, whichever way you want to write it. And let's do an Mn2+. In case you don't have a periodic table, calcium is 20. Bromine's atomic number is 35, I believe. Nickel's atomic number is 28. Thank you. And who do I got there? Mn 25. Okay, let's take a look here. So we'll start with calcium here, which is 20 with no charge. Once again, it has a +2 charge, which means our calcium here with a +2 charge would have 18 electrons, which would be 1s2, 2s2, 2p6, 3s2, 3p6. Or again, that is the same as Argon's configuration, right? Bromine here with no charge has 35. The -1 means it has gained an electron, which means it will actually end up at 36, which if you wrote it out would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, a little 3d10 action, and maybe like a 4p6, which is the same as krypton in this case. Any question on those two? Going to our nickel, which has 28 to begin with. A +4 charge would mean nickel in this case would have a 24, which would be 1s2, 2s2, 2p6, 3s2, 3p6. Now, if you just roll before we do anything, 4s2, 3d5. At this point, since it is a transition metal, we would want to take 2 electrons from here, right? And then we would also need 2 electrons from there as well. And that would give us the 4 electrons that would be lost. That would yield us a Argon 3D3 in this case. Again, this guy would also lose 2 electrons. Any questions on that one there? We're doing nickel. That is nickel. I did MN. Sorry, I laid up a chart, huh? That'll be 20. Thank you. That is 3D8. Thank you. There you go. So it would be a 3D8, which means that would then be a 5. There we go. Thank you. Or a 6. One of those, right? There you go. All right. Should use my calculator today, apparently. I'm going to try that again. All right. All right. So look at the right element. That would be 3D8 to start with. Thank you. And then that would then drop that correctly to a 6. Other questions on there? All right. The one I just did before, because I think I was looking at MN. MN2 plus here would actually end up with a 23. So that one would be the one that if we did it with no charge, would take me to what I counted originally there. 3p6, 4s2, and then the MN there is 5, right? In this case, we are going to lose 2 electrons. So we're going to drop those 2 right there. That would get us our Argon 3d5. I hope I counted that right. Any questions on that one there? Question on how to write electron configuration for things with charges, both representative and transition metals. Yeah. It's always the transition metals, so it's always these guys here. So it's basically transition metals from here to where zinc is and down. So all these guys will always lose off the S's. When we look at the periodic table while I'm standing here, there are certain blocks on the periodic table. So 1 and 2, group 1 and 2 coming this way, that is the S block. And there's 2 electrons you can put in there, 1 and 2 electrons. Over here, from group 3, where boron is to the N, that is what's known as the P block. And the P could put 6 electrons, 1, 2, 3, 4, 5, and 6. The D block is the transition metal, which is from here to where zinc is. And the D could put 10 electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. You can actually count it off. And down here, the lanthanides and actinides, these are the F block, which has 14 electrons, which you can count off 14 all the way across there if you wanted to. So you can use the period number as like the principal quantum number. So for example, if we were doing sodium, which we did earlier, you would start at the very top where hydrogen is. Hydrogen to helium is 1s2. Lithium to beryllium is 2s2. Boron to neon is 2p6. Sodium would be 3s1. You do have to know what you're doing so you don't screw up if you do it this way, because D start where? At what energy level? 3. This is D, which is actually on the 4. The D's are one behind the period number. This is 3D, 4D, 5D, and 6D. And F start on the 4th energy level. This actually should go right about here, which is 2 behind the period number. This is 4F and 5F. So if you really don't know what you're doing, you shouldn't count it off the periodic table because you will screw up probably in the middle there. But if you throw the zigzag guy back and forth, you'll probably always get it right, I would assume, in most cases. Question on that there. So always transition metals. So basically, once you dig into those D orbitals, and that's the end of your electron configuration, those will definitely be the guys that will lose those S's first. Other questions on that there? All right. I sort of bounced around, did a bunch of examples. Let's see where we're going to pick up. So we did a bunch of examples, which are basically what's on the notes. We did talk about the valence electrons here. Again, the valence electrons are really important. They are the outermost energy level. They're one furthest away from the nucleus. They're not held as tightly. You can get the number of valence electrons one of two ways. You could write the electron configuration like we talked about here, which again, the number of valence electrons here in this particular case would be those guys, the 2 and the 6, which would be 8. This would be the core electrons here. Or the number of valence electrons equals the group number on the periodic table. So group 1 is where lithium, sodium, and potassium is. Group 2 is beryllium, magnesium. Group 3 is boron, aluminum. Group 4 is carbon, silicon. Group 5, nitrogen and phosphorus coming down. Group 6, oxygen and sulfur. Group 7, fluorine and chlorine. And group 8, helium, neon, and so forth. So everybody has the same number of valence electrons as its group number for the most part. Transition metals, which are in the middle of group 2 and group 3, where again the Sc to the zinc and down. Most people consider it has like 2 valence electrons, those S's as they lose it first. That's typical of most people will kind of consider for those guys. The good news is we don't deal too much with those guys and bonding and stuff like that, so you don't have to worry too much about that. So once again, this is what we were just explaining, that you can really count off the periodic table. When we talk about groups on the periodic table, we do the representative numbering. That is group 1 coming down. That's group 2. Group 3 is over here. Group 4, group 5, group 6, group 7, and group 8. The only exception for valence electrons is helium. Has 2 valence electrons because frankly it only has 2 electrons, so it can't have 8. But everybody else there in group 8 will have 8 valence electrons. But once again, you can count off your electron configuration if you are careful around where the 3D is and the 4F and stuff like that. Again, I would probably recommend doing the zigzag approach. Would be the better move. So we won't do this as we did a number of examples. Now we talked about our transition metals and a couple of exceptions. There's our chromium and copper that we talked about, again, with the extra electron up in the D, 1 less in the S. And just to show you, there are some other common exceptions. On the left is what you would expect it to be. And again, on the right is what it has been found sort of experimentally. And you can see, again, something like PD, all those electrons in the S have basically been up to D orbitals and so forth. So most of these, again, as I mentioned, if you look at chromium and copper on the periodic table, kind of go down and in. A lot of those guys have a lot of exceptions to the normal electron configuration. For us in this class, you'll be responsible for just chromium and copper. You should still be aware that others, obviously below them, do have some exceptions, but the only 2 you'll be required to know will be chromium and copper. Anybody else there, even on this list, you could write normally, even though it technically is incorrect. You could write it normally based on that sort of zigzag back and forth way that we talked about. Any questions on that there? All right, any questions on electron configuration? By the way, the off-ball principle, as it mentions up on top, is the idea that electrons basically take protons one at a time, sort of the buildup principle. It's the same idea with electrons. They're added to the atom one at a time, lowest energy until all those get filled, next lowest, until all the electrons are basically distributed. Any questions on that there? All right, so let's talk a little bit about periodic table here. That is the periodic table. That is the periodic table over there as well. As you can see, there is a lot of different numbering on the periodic table. This one, for example, has got some B numbering. This one goes 1 through 18 as well. Pretty much every chemistry class you take, use again what is referred to as the representative numbering, which is the A numbering, although most people don't call it A. So group 1 actually starts with lithium, even though on every periodic table known to man probably you got hydrogen hanging out there, but hydrogen is actually not part of group 1. It actually does start with lithium. Group 2 is right next door, which is beryllium. Once again, we skip all the middle part, come over there to where boron is. That's going to be group 3. Group 4 next to it, group 5, 6, 7, and 8. So that is the numbering that we use here and in most chemistry classes. So let's talk a little bit about it. Elements in a column are sort of a up and down on the periodic table, are referred to as a group. Or if you're old like me, some people used to call it a family, not too much anymore. Most people call it a group. If you go horizontal there on the periodic table, left to right, that is what is known as a period. And there's 7 of them up there, which corresponds to really our electron configuration and our energy levels. There's 1 through 7 for the N number, and that's basically what those periods represent as well. The number up on top is what we talked about in the previous chapter. That is the atomic number, which, as you remember, is the number of protons, right? That is the number of protons there are. The number on the bottom is the atomic mass, which is not the mass number, right? It is broken up into 3 major categories. There are metals, which is typically to the left of the staircase that comes down. To the right and above that staircase are the nonmetals. On the staircase there, that is what is sometimes referred to as metalloids or semi-metals. Some books throw in boron with that as well. Some books don't. The 2 rows at the very bottom of there, the periodic table, which is not pictured here, those are also metals because they typically go kind of around the middle there of the transition metal region. What's that? They're lanthanides and actinides, which we'll talk about in just a second. We'll get to them. Yeah. But earlier we talked about this being group 1, group 2, 3, 4, 5, 6, 7, and 8. This is our friend hydrogen. That is lithium. Why is hydrogen not part of group 1? It is actually a what type of metal? What type of metal? What type of element is it? It's actually a non-metal. Yeah. So hydrogen is a non-metal, even though it is hanging out over there with the metals. Years ago, they used to throw hydrogen on both sides of the periodic table to thoroughly confuse students. They would throw it up over there near helium and over there next to where it is now. But hydrogen is actually a non-metal, which is why it's not part of group 1. Hydrogen has some unusual properties, one of which is it is one of the only elements that does not have a what? It doesn't have a neutron, right? So it has a proton, has an electron, no neutron, right? Everybody else got all 3 of those particles. We'll talk a little bit about metals. Metals are good conductors of heat and electricity. You could hammer them into sheets. You could pull them into wires. They typically have a very shiny appearance. For the most part, metals are solids at room temperature. The one exception is our good friend mercury there, which is in blue, right next to gold, which is Au. Hg is mercury right there. That is a liquid under normal situations. Also not the greatest of elements, which is why they take it out of chemistry labs. Non-metals, on the other hand, is pretty much the opposite of metals. They are bad conductors of heat and electricity. They have also a very different variety of physical states. Some non-metals are gases, some are liquids, and some are solids. So you got a little bit of everything happening with our non-metals. They're also opposite. They're dull, they're brittle, they're insulators. And again, for the most part in the periodic table, upper right is where you can find those guys of that staircase, along with, again, our hydrogen, which is over there. A lot of the non-metals are our diatomic molecules, our hydrogen, right? Our oxygen, our nitrogen, our fluorine, our chlorine, our bromine, and our iodine. So a lot of those guys we talked about, which actually are elements, and they're also diatomic molecules, are a lot of the non-metals that we have going on. So across section here, metalloids is pretty much on the staircase here coming down. And again, a lot of books will consider boron. I don't remember what yours does or not. But as that staircase come down, these are what are referred to as semi-metals or metalloids. These particular elements pretty much have properties that can really fall on either side. So the same metalloid can have properties that are very similar to what you find with metals, and that same metalloid will have some properties that are very similar to what you have with non-metals. And it makes sense based on their location. We kind of have metals heading towards non-metals, sort of our transition point. So these guys, you know, can kind of fall on either side of the staircase in terms of their properties, you know, as you go through it. Some have special names, some of these groups. First off, group 1, which again starts with lithium and down. That is our alkali metals. Right next door, beryllium and all those guys in group 2 is our alkaline earth metals. Out to group 7 there on the periodic table, those are our halogens. Group 8 on the periodic table are noble gases. Again, also why hydrogen not part of group 1, because those are metals, and again, hydrogen not being a metal. Alkali, alkaline, I don't know how fancy of a word that is, but that basically means basic. And that is where a lot of strong bases come from. Things like sodium hydroxide, potassium hydroxide, calcium hydroxide, strontium hydroxide. So a lot of really strong bases come from group 1 and group 2 on the periodic table. And that again is what the word alkaline means. So if you ever come across instructions that say, make it alkaline, it means make it basic. Like if you're doing your experiment in 200B. So you do need to know where the alkali metals are. Alkaline earth metals, the halogens, the noble gases. Stuck there between group number 2 and group number 3 on the periodic table are transition metals. So between those two groups, all those guys on the bottom are transition metals. One thing about transition metals are they can make a variety of positive charges. So the same element can make, for example, +1 and +2, depending on the situation. And the earlier question is these guys here, lanthanides and actinides. If you follow the numbering here, this is 57, that is 72, that is 58, which means these two rows actually go right there on the periodic table. And they don't put it there, otherwise it's a very wide periodic table. That's why they're also sometimes referred to as inner transition metals. I've only seen one periodic table when they actually put it in the right location. They needed the entire wall, shifted the periodic table all the way over, and you put those two guys there. So these guys technically do go in here. If you follow the numbers, they follow lanthanide and actinide, which is why they're referred to as those two sort of names. Any questions on that there? Obviously, the noble gases are also sometimes referred to as rare gases. They are, again, what are referred to as being chemically inert, which means they do not react with other things. They will react with themselves, but not other things. And as we talked about a little bit before there, that's essentially what the goal of bonding is, and what everybody wants to achieve is that stable sort of situation like they are, which is why they want to end up with the same electron configuration as our noble gases. Transition metals and our lanthanides and actinides. Any questions on periodic table where things are located? So obviously you need to know which way groups go, which way periods go, the names of the special groups, where the transition metals are, where the metals are, non-metals and metalloids are located. Any questions on any of that there? So let's talk a little bit about periodic trends. We're going to talk about a few periodic trends here. Ionization energy, electron affinity, and atomic radius. And we're going to also add our friend electronegativity to it. That's actually out of chapter 3, I think. It's the only thing from chapter 3 that she has to worry about for the first exam. So let's talk a little bit about each of these things. Ionization energy is the energy that's required to remove an electron from the gas phase. So if you're not sure, electrons actually come off one at a time. So we don't lose all the electrons at once. They actually come off one at a time. So if we had something like our friend magnesium, the first thing that would happen is magnesium would ditch an electron and it would come off. The next thing that would happen is that magnesium that lost an electron would then lose a second electron. Then the second electron, we would lose a third electron and so forth. Every time an electron comes off, the energy required to do that is what is known as the ionization energy. This would be known as the first ionization energy. This would be the second ionization energy. This would be our third ionization energy. As you can see down there, is it easier to remove the first electron or the second? It is easier to remove the first electron. We can see that by looking at the numbers here, 735 to 1445 to try to remove the second electron. What happens to the overall size of magnesium when it loses an electron? Does it get larger or smaller? It's a 50-50 shot there. So if I lose electrons, am I going to be larger or smaller? I'm going to be smaller. Yes. So like I have 12 electrons, I'm happy. I lose an electron cloud gets smaller, right? When I gain an electron, what happens? It goes the opposite way, right? You gain electrons into your electron cloud, you become larger. So a cation, which is the positively charged ion, will always be smaller than the neutral guy, and the anion, which is the negatively charged ion, will always be larger because it's gaining electrons. In addition to my wonderful display of becoming smaller, my outer electrons at that point then become closer to the nucleus, right? So now they're closer to the nucleus. Everybody's closer to the nucleus. That means the electron is going to be held a lot tighter, which means it's going to be harder to remove the next electron. And again, we see that you need like twice the energy to remove it, right? I pop off the second electron, my electron cloud then gets smaller again, moving all my remaining electrons closer to the nucleus, making it super hard to do. I now need like 10 times the energy I needed for like the first electron to pop off the third electron. And if we look at the electron configuration here, 1s2, 2s2, 2p6, 3s2, magnesium has how many valence electrons? 2, yes. Those would be right there, the 3s. These again are what are referred to as core electrons. So we're able to pop off the first one, not too bad. The second one gets a little harder. But now if I wanted to pop off the third one, what electrons am I into now? I'm into the core electrons, which were closer to the nucleus to begin with, even more closer at this point once you dump the extra 2. And it doesn't happen. That's why we don't see magnesium ever becoming a +3 charge, because energy-wise, it is not going to occur in a normal situation. Because of that, those electrons are now way too close to the nucleus. Yes. You could, in certain situations, you could try. I don't know, you know. Yeah, you need a lot of energy to do it. I mean, that's per mole, right? So, you know, you don't just have like 1 mole usually, right, in a sample. So you might have a lot. So not going to happen. I'll just put it this way, not going to happen in normal conditions. I suppose in theory you could force it to happen in theoretical situations. So when we do get to our core electrons, really because they're closest to the nucleus, they're held tightly, and they get even closer to the nucleus as we continue to sort of drop off those electrons. Once we really get to that core electrons, it becomes energy deficient to try to make that occur. So the general trend in ionization energy is it increases as you go from the first electron to the second to the third. in general on the periodic table, it increases as you go up and to the right. Ionization energy increases, and it decreases as you go left and down on the periodic table. So much easier to remove an electron left and down than it is right and up on the periodic table. Any questions on that there? All right, we're gonna, I think, lay it